All right, AP Calc BC, Unit 2, Day 1. This unit is going to be all about limits, which we learned about in Calc AB, and we'll learn some new things, but there'll be a good amount of review. So, just starting off with kind of basic understanding limits, here's kind of a weird piecewise looking graph. And one side of the limits have this little superscript number or sign, positive, negative, and that means from the negative side. Okay, which means from the left, right? From the left. So we're coming in like this. So at -2, right here, if we approach it from the left, the limit, the value that the y value is approaching looks like it's 1, right? From the right side, right? So this is from the right side, the positive side. We're approaching it like this, and it approaches the value of 2. Now, a two-side limit, which is a lot of times what we're dealing with, requires that both one-side limits agree. So, in this case, the limit does not exist. Or we might say there's no limit. And last year, I used an example about both your mom and your dad agreeing on a curfew. If they both gave you different times, and hey, there is no curfew. I don't know if that argument will work well, but mathematically, it makes sense. How about x approaching 1 from the left side? The value approaches, it looks like 3. From the right side, it approaches 3. So the overall limit is 3. Even though the function could have a hole there, limit still exists, or even if the value of the function is a different value. So even though, but f of 1 equals 1. So the limit does not need to be the function's value there. Okay. It's where the graph should be, maybe where it looks like it should be, right? Where the graph is going. So sort of a basic, simple approach to limits. Now, there's a formal definition, which I avoided last year in Calc AB. I'll go ahead and make an attempt right now to explain it. It's a little, it takes this very simple idea and, makes it seem much more complicated. But for mathematical purposes, it is, a more, precise way of defining this. So assume a function f of x is defined near c. So that's an x value. And f of x has a limit L as x approaches c if and only if given any positive number e or epsilon, Greek letter, however small we want it to be close to this L value. So I guess that's how I'm gonna write. I'm gonna say, you tell me how close you want f of x to be to L. So you tell me how close you want f of x to be to the limit L. All right. You give me a positive number, epsilon. How close do you want it? So for instance, let's say, well, I want it to be within 0.5 of L. Now, if you tell me that, then I should be able to find a range of x values, C, close to C, that will satisfy your desired closeness. Okay, so I should be able to come up with some delta plus or minus to C that all the values in here will be at least 0.5 away from L. So let's just make up a number and say, it's like 0.25. I found within, if you're within 0.25 of C, your f of x value will be between 0.5 of L. Okay, so that's just kind of a simple example. Now, what we could do, if the limit actually exists, is that we should be able to keep playing this game, and you keep giving me tighter and tighter restrictions, and I keep coming up with new and new deltas, which will probably inevitably be closer and closer to C. And for the limit to actually exist, we should be able to do this for any range. Okay, you should be able to give me any epsilon as small as possible, and I should still be able to come up with deltas that satisfy your requirement. Okay, so another way of saying that is we could say if there is any value of C for any delta, and so this is distance. So given an epsilon value, okay, given an epsilon value that's positive, we can find a delta that's positive also, so that if x is within delta of C, this is going to be true. Now, what another way of saying such that for all x is within delta, I guess I could use the delta of C. Now, another way of saying that, to say that our x is within delta of C, is to say that the distance between x and C is less than delta. So this is just a different way of writing that idea down. And then we could say also that the distance between the function and the limit L is going to be less than epsilon. Okay, so if we can do this, then the limit actually exists. Then we've proven that the limit exists. So in simpler terms, as f of x is close to the limit L, x of x will get close to the limit L as we get close to some value C. So anyways, it's kind of a, kind of a different way of thinking of it. So, I mean, just going back here, I guess we could add this range around C where any value will give f of x within, and our first example was 0.5, range around C where any value will give f of x within 0.5 of L. Now we make epsilon smaller, right? And need to be able to do for any range if the limit exists. So, okay. So limit as x approaches 3 of x squared equals 9. Why? Because as close as you want x squared to be to 9, I can find a value close to x that will give you that answer within that close. So now there's different ways that we're not going to necessarily use that in our class for problems, to help us solve problems. But we're going to use some other techniques. So if possible, we could just plug the value in. Like this one right here, if I say, okay, let's call that substitution. If I just plug 3 in here, 2 times 3 is 6 plus 1 is 7. Now, sometimes that's the answer. Sometimes it's not. But in this situation here, that will actually work for any continuous graph. And that gets into another definition of continuity. But this graph right here is just a line. Go up 2 over 1. And you go up 2 over 1. Right? And so there's your line, up 2 over 1. And so this is just a line. And, from the left side, we're approaching the value. And from the right side, we're approaching the value. And yeah, sure, it's just whatever the value of the function is. Okay. So if it's a continuous graph, you can simply just plug the value in and substitute it in. But, it's going to usually be more complicated than that. If it's not a continuous graph, or that doesn't work, we could use a graph or a table or some other technique. So for instance, let's say that we have a graph and there's a hole in the graph. And the graph might look like a parabola and there's a hole in the graph, let's say at 2, 6. Then the limit as we approach x equals 2. So now if you plug 2 into this function, it's probably going to give you something bad like a division by 0 or 0 over 0 or something like that. And so that's not the answer, obviously. But as we approach 2 from the left and right, the limit is 6, right? The answer is 6. Now, let's look at this graph. Actually kind of has this kind of look to it. Now, what's going to happen is if you do just substitute the value in, which I usually just try and do, you get x cubed is 2 cubed is 8 minus 8 is 0 over 0. So that's probably what's going to happen if you have a hole in the graph. You get 0 over 0. Now, what we could do is we could rewrite the limit, and what might be happening here is that you have a hole in the graph. And so if you can factor the top and bottom, or if you guys remember how to factor a difference of cubes, you could use synthetic division and rational root theorem for that. But a cubed minus b cubed equals a minus b Okay, so if we factor this difference of cubes, you might remember SOAP, but that only helps you with one thing. That only helps you with the signs. But it's whatever's being cubed, and then you square it, and in the middle you multiply it together. You just multiply those two things together, and then it's same, which is pretty opposite of negative, always positive. So this is x minus 2, x squared. I usually fill this in first. 2 squared is 4. Multiply them together. Same, opposite, always positive. The bottom, we factor it. And that's your hole. That's what's causing the hole. So if we now reevaluate the limit with those gone, you get 4 plus 4 plus 4 is 12 over 2 is 6. Right? Now you could use, I'll show you guys some other ways to do it, but you could use a table of values to kind of like investigate it. I mean, this is probably the best way. You could use a graph to kind of try and get next to it. But so this is same, opposite, always positive. You could use the rational root theorem to get that. It's a lot more work, but piecewise, kind of like the graphs we did above, we were just using a graph. There are some other situations where the limit as x approaches sine of 0, if you plug 0 in, you get 0 over 0. And we call this the indeterminate form, meaning you cannot determine the answer from it. Okay, so what does it equal? Well, we can't really factor the hole out either, but there is a hole. So I mean, I could show you on a graph If we put this in sine x divided by x, I think we should be in radian mode. Okay. We go window -5 to 5. No, just start with that. So here's the graph. And that's kind of what it's doing now. Let's play with this a little more. So it kind of looks like, sort of like a sine curve, but the amplitude is changing, and as x gets bigger, positive or negative, the whole answer is going to get smaller because you're dividing by bigger things. So, and it doesn't really look like there's a hole in the graph, but at 0 there is a hole in the graph. Now you'd be like, oh, let's zoom in really close, see if we can see the hole. Well, technically, a point is infinitesimally small, so a hole is going to be infinitesimally small, and I don't think we're going to be able to necessarily see it, right? But the interesting thing is, if you go trace, trace is where you could be like, oh, it looks like the graph is going towards 1 from the left and the right. You see that? So we can kind of use that to be like, oh yeah, I think the limit is 1, even if there is a hole there. Now here's the way you can confirm there's a hole. You can do second calculate value and type 0 in, and look at this. This is nothing for the y. So the answer is 1. Okay, and I'm going to let you guys use that fact for some homework problems. So sine x over x, which is kind of weird too, because the value of sine actually gets close to the angle that you're plugging into it for small values of x. This one here, if we just plug 2 in, we get 4 over 4 equals 1. That's a different situation. That's a continuous graph there. So the sandwich theorem, which is also they call it the squeeze theorem. Spell that right. So here's an interesting graph. And so you can say, well, if I plug 0 in, I get 0 times cosine of like 1 over 0, which means it's going to go to like infinity. So what's the answer going to be? Like cosine, and you might intuitively kind of be able to tell me what the right answer is, and that's fine, but you got to be able to show work for it. So let's see if we can see what this graph looks like. X to the 4th cosine of 1 over x. We can do zoom 6 just to start with. Where is it at? There it is. Okay. Now it looks almost like a parabola, but what we might be able to do is see what's happening closer in there. See what's happening here. Oh, kind of interesting. So, I mean, it looks like, I don't know, we can maybe even do closer, see what's going on there. It's not a parabola. Definitely not a parabola. It went below and then back up or something. So let's see if we can see what's going on here. Oh. And then it's doing it again there. It's kind of interesting. So, anyways, I'll show you another graph in a second. So what we want to do is, we can focus on, okay, well, cosine of x itself is definitely between -1 and 1, right? That's the range of cosine of 1 over x. Like cosine of anything is going to definitely be between -1 and 1. So then we can multiply the left, right, and middle by x to the 4th. Like algebraically, that's okay. And it's for sure a positive number, so we don't have to worry about flipping the inequality symbols, right? So this has to be true, right? And then we say, well, if we take the limit of this as x goes to 0, this is going to go to 0, right? And this is going to go to 0, right? And if this is always in between these, well, then this has to go to 0. It's squeezed in between these values of 0, right? So it's got to be going to 0. So if the limit as x approaches negative x to the fourth equals the limit as x approaches 0 of negative the fourth, I guess these should be like, this should be paused right here, this little typo. And it equals 0, then what's in between has to equal 0, right? Now, here's the interesting thing. This graph, one of these graphs is a quartic, which kind of looks like a parabola, like this, and the other one's an upside down one. And what would happen is if you graph this, you could tell that this other graph right here is going to start to do stuff like this. And you kind of got that feeling, right? From this graph right here. But if we were to add x to the fourth and negative x to the fourth to this graph, look at that. It goes right here, and there's this other one right here. And if you're to zoom out, you just continue to see this pattern. And it would be always in between it, right? I mean, we for sure know that this is always in between these graphs, right? So if we can find a point where both of those graphs go to the same value, then the point in between has to get squeezed into that value. Continuous. F of x is continuous at x equals a if and only if the limit. Okay, so this is definition of continuity. Okay, and this is the time where the value of the function matches the limit. So we've seen ones where there's a hole or there's a jump. Well, that's not continuous. So if the value of the function matches the limit, then the function is continuous at that point. Okay. Now, in behavior is when we take limits to positive or negative infinity. And that's often where we get horizontal. That's usually the way we find horizontal asymptotes. Some graphs don't have horizontal asymptotes, some do. So we'll talk about that more, I think, tomorrow. So here's another example using substitution. If you plug 0 in, you get 16 minus 16 is 0 over 0, which is indeterminate, right? So what we're going to try is to, see if we can identify the hole. So to do that, we're going to have to try and factor top and bottom. But the top needs to be multiplied out first and combined together before you can factor it. And so this is the kind of work you would show. And then we could factor an x out of what's on top and x out of the bottom. That's the hole. And then we plug 0 back in and we get our answer. So that's the way we've been doing that. Now, determining it graphically and then confirming algebraically. So some of the problems on the homework ask you to do this. So this is what we're going for here. So I would first maybe try and get a rough view of what this graph is going to look like. It's going to have, let's see. I don't know. It's going to have vertical asymptote maybe somewhere, but you might think these are both vertical asymptotes, but they might not be. So let's graph this function now. Parentheses, definitely need parentheses. Around the top, x squared. I'm putting x's in for the t's. Plus 2, close, x squared minus 4. Window, let's do -5 to 5, -10 to 10. Okay, now that's a vertical asymptote usually on my graph. And then over here at x equals +2, there isn't one. So, rough sketch of this, vertical asymptote at -2. And a positive 2, I don't know. You might have thought you might have got one, but it didn't really look like it. So in behavior, by the way, if we go to infinity, these are the dominant terms, and they're going to go to 1. So the horizontal asymptote is going to be positive 1. Y equals positive 1. And so then the graph looks like it's going like this. And then over here, it's going, it looks like it's crossing somewhere over there. Whatever. Okay. Now, if we were to, use the graph, we could say, well, let's see, let's do the trace button and say, let's get really close to x equals 2. So x equals 2. Y looks like it's going towards maybe 0.25, and it's got to be true from both sides. I mean, I would guess it's like 0.25 just by kind of looking at the graph, right? But let's do some calc value and plug in 2, and it's giving us the blank thing. So that must mean there's like a hole or something in the graph. So that's graphically. Now confirming it algebraically is the way I was showing you before. So if we take the limit as t goes in, as t goes to 2 of t squared minus 3t plus 2 over t squared minus 4. If you plug 2 in, you get 4 minus 6 is negative 2 plus 2 is 0. 4 minus indeterminate form. So let's try factoring and see if there's a hole there. T plus 2, t minus 2. This is going to be t and t, and negative 1 and negative 2. And so there's the hole. And then if we plug t equals 2 back in here, we get 1/4. It worked. Okay. So this is your assignment out of your book. And check your odds in the back of the book. And read the directions. Use the techniques that they want you to on different kinds of problems. That's it.